In this section, we explain the heat capacity and thermal conductivity of materials using the Phonon theory of atomic vibrations. We will use the equipartition theorem to find a most useful form of the heat capacity for solids. For classical systems in thermal equilibrium, the energy is shared equally among all its various forms, which is known as the equipartition of energy. This means that 1/2 kT is distributed for each dimension of its kinetic energy and its potential energy. In physical chemistry, this is typically used to show that the kinetic energy of a monatomic gas is 3/2 kT. 1/2 kT comes from each of its kinetic energy terms, the x, y, and z dimensions. The heat capacity at constant volume is defined as the derivative of the total energy with respect to temperature. This quickly gives us the heat capacity of a monatomic gas is 3/2 kB per atom. For atoms in a solid, we not only have the 3 dimensions of kinetic energy, but also 3 dimensions of potential energy for each atom, where each of these can be thought of as the spring potential energy of the bonds. Energy is stored in each of the x, y, and z dimensions, providing another 3/2 kT. In solid materials, where every atom has neighboring bonds that also store thermal energy, we have the heat capacity per atom is 3 kB. This is known as the Dulong-Petit heat capacity. The Dulong-Petit heat capacity of about 25 joules per Kelvin per mole is a very good approximation for many materials. The deviations in room temperature heat capacity are found in materials with light elements and strong bonds, such as diamond, beryllium silicon, or hydrogen-containing materials. At low temperatures, the specific heat capacity of a material deviates from the Dulong-Petit value due to quantum size effects. We can estimate the heat capacity of lattice vibrations at low temperature from the Debye model. The internal energy of all the phonons U can be calculated by integrating up the energy per phonon, h bar omega, times the density of phonon states, G, times the probability distribution function, P. For phonons, we need to use the Bose-Einstein distribution function, shown here, where once we do the integration for the energy and take the temperature derivative for the heat capacity, we get the Debye heat capacity for phonons. The Debye heat capacity, shown here as a function of T divided by Debye temperature, is actually quite close to the Dulong-Petit heat capacity for most materials at engineering temperatures. It is within 20% of the Dulong-Petit heat capacity for temperatures within half the Debye temperature. Only very hard, stiff materials such as silicon or diamond have Debye temperatures high enough for the heat capacity to be affected at room temperature due to the quantization of phonon states. Phonons can also be used to understand the thermal conductivity in a material. In addition to electrons carrying heat, phonons or atom vibrations can also carry heat. Like we did for electrons, we can use a simple kinetic model for phonons. The conductivity is 1/3 times the amount of heat the phonon carries, or the heat capacity, the velocity of the phonon, and the phonon's mean free path. For a rough estimate, we can use the Dulong-Petit heat capacity of 3 kB per atom, the speed of sound for the phonon velocity, and an average mean free path. Scattering of phonons is treated similar to that of electrons in terms of describing it with a scattering time, where different scattering mechanisms can be combined using Mathiassen's rule. Like we saw for electrons, phonons can scatter off atomic vibrations, although in this case, atomic vibrations are other phonons. Phonons interact due to their anharmonicity, which is characterized by the Gruneisen parameter gamma, which is related to the thermal expansion coefficient alpha. The vibrations increase with thermal energy, so the scattering rate is proportional to temperature, leading to a thermal conductivity inversely proportional to temperature. Strong, hard crystals with a high speed of sound, such as sapphire or MgO, have very high thermal conductivity that decreases with temperature approximately as 1/T. Phonons also scatter off any disruption in the crystal, including point defects such as vacancies, interstitial atoms, or substitutions, but also dislocations and interfaces. In complex materials, the phonons scatter more frequently from defects rather than other phonons, so the phonon mean free path is small and temperature independent. Thus, materials like silica glass, SiO2, polymers, PMMA, Large and complex crystal structures, here barium, gallium, germanium clathrates, and heavily defective crystals such as YSZ have very much lower thermal conductivity than simple crystals, and the thermal conductivity is much less temperature dependent or even flat around room temperature.